Efficient cargo handling at loading and discharge ports is a critical area in the effective operation of a competitive tanker fleet. To help meet the demand for increased discharge rates, modern ships are fitted with powerful centrifugal pumps. But with the best pumping plant, consistently good results can only be achieved if ship's staff have a basic appreciation of the characteristics and constraints of their particular system. Essentially, a centrifugal pump consists of an impeller wheel turning in a casing, with an inlet at the center or eye and an outlet at the throat. When the pump's working, liquid from the inlet is spun round by guide vanes on the impeller and thrown outwards at high speed by centrifugal force. This acceleration creates low pressure at the eye, high pressure in the case, and a powerful flow of liquid through the pump. Pumps built for cargo work are sizable units, operating at hundreds of revs a minute and capable of shifting thousands of tons an hour. Ships normally have 3 or 4 of them, fitted as low as possible in a pump room between the cargo tanks and the engine room. Flow through a pump, as we saw, depends on various pressures. Low pressure at the inlet, high pressure developed in the pump, and whatever back pressures encountered en route. But pressures vary with the specific gravity of the liquid, so pump performance is best defined without reference to pressure, in units unaffected by specific gravity. These are the flow in cubic meters an hour against the resistance, head, in meters. To explain the significance of head, let's look at a simplified pumping diagram. Assuming an adequate supply on the suction side, flow in this situation depends on the impeller's speed and nothing else. But if the discharge pipe were vertical, of course flow would immediately be reduced by the effect of gravity. If we take a branch off low down, the reduction's minimal. Further up, it's worse. Up again, worse still. And so on, till eventually the effect of gravity stops the flow altogether. Now the height where this happens, the head, will be the same whatever we pump. The pressure at the base of the column varies with the specific gravity of the liquid. It varies appreciably between, say, seawater and kerosene, but the head remains constant for any liquid. We can show the relationship between head and flow on a straightforward graph. H for head, and the flow by Q for quantity. Starting from the bottom again, we measure the height of the first outlet, measure the flow, and plot the result. A low head and a good flow. Now we measure the next one. Measure its flow, and plot the result again. A greater head and a lesser flow. Now plot the next one, and the next one, to the maximum head, and the no flow state. Now, with the plots joined up, we have a performance, or HQ curve, for one pump at one given speed. Typical figures for a VLCC: 0 to 150 meters head, 0 to 5,000 cubic meters an hour for flow. But these curves apply to the pumps alone. They take no account of the inherent resistance within the ship. Frictional head losses in the lines, round bends and through valves, plus a mean figure for the lift to the deck. All these can be calculated, and from the results we can modify the pump figures to find the true performance curve after the resistance within the ship's been overcome. Obviously, we drop down the H-axis a bit now that some of the pump's potential's been used up negotiating the system. This new curve is the manifold curve. Each ship is supplied with a family of them, covering her range of pumps and pumping speeds. Manifold curves are the ones that really matter. They describe precisely the ship's capability during every discharge cycle. A proper understanding of their derivation and implications is fundamental to the intelligent use of cargo pumps. Manifold curves, then, give us a pumping profile for the ship, which stays the same wherever she goes. But the situation ashore differs widely from port to port. No two installations are alike, and each one presents its own resistance to a discharge. Back on our graph, we can see that the head ashore could be plotted on the same axes. Obviously this time, though, head increases with the flow, producing this sort of curve. The greater the flow, the greater the head. It may be a steep curve or a shallow one, but either way, where the shore curve intersects our manifold curve, shows us the best possible discharge rate for that particular ship at that particular port. During a discharge, control room instruments will give us an idea of the kind of shore curve we're pumping against. And of course, the sooner we know, the better. Take the question of how many pumps to run. This is a performance curve for 4 pumps, working in parallel. Reasonably, it suggests increasing the flow by an equal amount with each pump. 1, 2, 3, and 4. 4 times the flow. But in practice, this can never happen. If a shore curve, even a shallow one, is superimposed, we can see the diminishing throughput we get from each successive pump. And of course, the steeper the shore curve, the worse the effect. By the time it's here, for instance, there are really significant reductions. And in a case like this, there's little to be gained by running more than the first 2 pumps. This is a common experience regularly met in practice, and just one where the graphic information on performance curves can help you plan ahead before the actual discharge. Now for an example where we can prevent damage to the pumps themselves. A dangerous situation may arise if pumps are run in parallel but at different speeds, as quite a small drop in revs can produce a surprisingly large reduction in throughput. In this extreme case, pumps 1 and 2 are creating a head greater than the maximum possible for pump number 3 at its reduced speed. So if we run number 3 at that speed, there'll be no flow at all. It will still turn, of course, but all its energy will be converted to heat, and expensive damage can quickly result. So we have to remember that when pumps are running in parallel, there should be no variation in their individual speeds. Throughout any discharge, it's important to ensure a sufficient supply of cargo at the pump inlets. Our last curve alerts us to a potential danger here when the tanks are low. This is the curve for net positive suction head, NPSH. It shows us the minimum head of cargo necessary at the inlet for the pump to maintain suction. This head is a combination of the height of cargo in the discharging tank plus any positive inert gas pressure on top. As the tank approaches draining condition, the available head tends toward the minimum required. And at this stage, cargo at the low pressure inlet may begin to vaporize. When this happens, bubbles of hydrocarbon gas are drawn into the pump. We can see them properly in this cutaway model. Once inside the casing, the bubbles collapse under the high pressure and liquid rushes into the empty spaces. This effect's called cavitation, and it happens with such violence it actually erodes metal surfaces inside the pump. The results show up on this impeller, which in its worst places has been eaten right through. Warning of cavitation comes from the tachometers, which fluctuate wildly as the pumps start to lose suction. If this should happen, unless suction can be increased or the pump slowed down, discharge must be reduced immediately by partly closing the appropriate discharge valves. If we look at an NPSH and a manifold curve together, we can see how closing a discharge valve works. Suppose this were the situation. The minimum suction head necessary at the pump inlet now is here. So as soon as the available head falls below that line, cavitation will begin. But by partly closing the discharge valve, we can bring ourselves back to a new position on the NPSH curve, where the necessary minimum is just low enough again to resume a reduced but safe and steady flow. The significance of these performance curves can't be stressed too often. This elementary introduction seeks to give everyone concerned some insight to their importance in successful pumping practice. We've seen how centrifugal pumps work, looked at their potential on the manifold curves, the limiting effect of the shore curve, and considered a few of the implications on day-to-day operating. All the relevant information is available on every ship. Efficient cargo handling depends on its intelligent application.